couple of things to finish up about Chapter 20, which was looking at circuits in the macroscopic viewpoint of circuits. The homework you're going to have that's due on Friday does have a couple questions on power. So power is what? Power is what? Say again? Work divided by time, right? It's work per unit time, or just more generally, it's the energy delivered. You can think of it as sort of a change in energy per unit change in time. How much energy is being delivered or taken away per unit time, okay? And we can apply that to electric systems, in particular circuits. If you have a battery, for example, and by the way, you may run into this. We've been drawing kind of cartoonish pictures of circuits, but you may run into more schematic diagrams where a battery is represented by a little line and a big line, and the little line is the negative terminal and the big line is the positive terminal. And then the connecting wires are just lines. And if you have a resistor in the circuit, we represent that with a little jagged line. And so this has some resistance, R, which we talked about last time. And this battery has some EMF. And so you can think of it such, for instance, a battery connected to a light bulb, some thin filament that's going to cause a large electric field inside the filament and a large potential difference. And so there's going to be energy radiated away, right? The battery is delivering energy to the rest of the circuit. And then in the steady state, the amount of energy being delivered by the battery per unit time is the same amount that's being dissipated away as thermal energy, right? The light bulb gets hot, and it gives off thermal energy. And so in the steady state, the amount of energy in is equal to the amount of energy out per unit time. So we can talk about the amount of power delivered. Power, we think of this in terms of change in energy, or we can think about a change in electric potential energy per unit time. We can relate electric potential energy to electric potential by saying it's the charge charge times delta V. And then we can think of this as an amount of charge flowing per unit time times delta V, but charge per unit time is what? Coulombs per second is what? That's current, conventional current, right? So power we can write as conventional current times delta V. And this is just a general formula for power delivered to electric elements in a circuit, okay? Current times delta V. If you want to think about the power dissipated by a resistor, okay, well, first of all, the power delivered by the battery would be then I times the EMF, since in an ideal situation, the EMF is equal to the potential difference across the battery. The power delivered or dissipated by the circuit, in the power that's being radiated away in the form of heat, is, well, since we know the potential difference we saw last time, Ohm's law, potential difference is the current times this quantity, the resistance, or we could also write that as current is equal to delta V divided by the resistance. Then for a resistor, we could also write this as, if we substitute in the current, we could say it's delta V times delta V over the resistance, or delta V squared over R. Or alternatively, I could substitute in the potential difference if I knew the current and say that this is I times IR, or I squared times R. Okay, so these formulas are only for resistors. This one is true all the time. Okay. You'll have a homework problem or two that deals with this. The key idea, again, is that energy conservation in the steady state means the total energy delivered by the battery is the total energy radiated away by the rest of the resistive elements in the circuit. And we have formulas for calculating the resistance and formulas for calculating the power. That's pretty much all I'm going to say. You should take a look at this in the end of Chapter 20 and read up on it before you try the homework that's due on Friday. And just one other thing that you might run into, and you may, if you're taking a circuits class or an electrical engineering class, you may have already seen this being applied. The loop rule and the node rule still work. Okay, it's just that in some cases we may not be. We've used them to calculate electric fields inside elements in a circuit, and that's fine. And then we can use those electric fields to calculate currents, for example. In some applications, in most sort of macroscopic applications, you may be just more interested in finding the current directly, okay? But you could still apply the loop rule, okay? So for example, if I go round trip through this circuit, very simple circuit here, then I would say, okay, round trip potential difference is equal to 0. I'm going from the negative to the positive terminal of the battery. I'm going to have a EMF. I'm going in the direction of the electric field, so if I'm going electric field pointing that direction, so I'm going in the direction of the electric field when I go across the resistor, assuming that the potential differences across the thick wires are approximately 0. Then the only other potential difference I'll have is when I go across the resistor. I'm going to have a potential drop, so I'm going to say minus the delta V across the resistor minus the magnitude of the potential difference across the resistor. Back to where I started from, that's equal to 0. But delta V is equal to the current times the resistance, right? So I could just write EMF minus I times R is equal to 0. And then just solve directly for the current in this particular circuit. Okay, so this is a simple example, but the same rules apply if you have lots of different resistors in the circuit. They may be in series. They may be two branches in parallel where you have a junction. Okay, and we're not going to do too much of this, but it's again just another application of the same rules we've already seen. If you have an EMF, say an R1, resistance 1, resistance 2, and resistance 3, you would have a current through this branch, call it capital I1, call this current capital I2, and this current capital I3. From the node rule, what do you know about the relationship between the currents? I1 is equal to I2 plus I3, right? So if you're trying to solve for those three currents in this particular circuit, you have three unknowns here. You'd have to have three independent equations. We've done applications like this before, but you may see them in terms of resistance and current rather than electric field and length. So you could write loop rule equations. For instance, one loop might go through the EMF through R1 through R2 and then back to where you started from. So that loop would give you an EMF. You have a potential difference, a potential drop across this first resistor, which is equal to the magnitude I1 times R1. You'd have a potential drop across the second resistor equal to minus or I2 times R2. And then you're back to where you started from. You set that equal to 0. What other loop could we choose? There's two other possibilities, right? Okay, so we could start where? Start at the battery and go through I3, right? And that would give us EMF minus I1 R1 minus I3 R3 equal to 0. Or what's the other one? Yeah, you could go through this loop, right? Again, we don't have to go through the battery necessarily. Round trip potential difference for any choice of path has got to be equal to 0. So if I go in this direction, in the direction of the electric field through this second resistor, I'd have a negative I2 R2. But if I go in the opposite direction here of the electric field through this resistor 3, I'd have a plus I3 R3. Okay, set that equal to 0. You would need that node equation and any two of these loop equations in order to solve for the currents. Again, this is just it's the same thing we did before with electric fields, loop rule, node rule. It just looks a little different because we're putting it in terms of conventional currents rather than electric fields. But it's the same thing. You might run into this in later applications with all kinds of more complex circuits, but it's the same basic rules being applied every time. Okay? Questions here? I'm not going to go through it and solve it. We could do it if we knew the resistances in the battery and the voltage across the battery. We could solve for these currents, but it's just algebra at that point. Okay? Questions? Okay, that's it for chapter 20. So we'll starting a new topic today, and let's sort of sum up where we've been so far, what we've seen so far. One of the first things we talked about way back in the beginning of the semester, kind of the central idea of this course is the relationship between charge and field. Okay, and we said that charges create fields in space. And then if you have fields in space and you place a charge at a particular observation location, that field is going to affect or exert forces on, essentially, other charges. Okay, so charges create fields, fields affect charges. That's the basic idea. Okay, we've seen ways in which this is done. We can say how charge makes a field, and we've seen a couple ways of doing this. Well, lots of ways of doing this, but basically they flow from, if you have just a charge, then it's going to create an electric field. And the electric field, we said, is 1 over 4 pi epsilon 0 Q over r squared times r hat. And then we use that lots of different ways to find electric fields due to different charge distributions, charge rods, charge rings, charge spheres, what have you. Okay, but it all kind of flowed from here. If the charge is also moving, say charge times a velocity, then the charge makes a magnetic field. And that is mu naught over 4 pi QV cross r hat over r squared. Okay, and again, we could apply that to lots of moving charges in a current, current rings, current loops, magnetic dipoles, what have you. But it all, again, kind of flows from that basic idea. And so charges make fields in these ways. Then we can think about how fields affect charges. We've talked about if you just have a static charge and you have an electric field, then it's going to exert an electric force on that charge, which is just equal to the charge times the field. Okay? The new idea that we're going to talk about now is that if you have a charge, how do magnetic fields affect it? How do magnetic fields exert forces on charges? And much like how you need to have a moving charge to produce a magnetic field, it turns out you need to have a charge moving in order to feel a magnetic force on it. So we can say the magnetic force, I'll just introduce the relationship and then we'll talk about it, is QV cross B, yet another cross product. Okay, it's the charge times the cross product of its velocity with the magnetic field. Okay, so what this is saying is if you have a magnetic field, let's say we have a magnetic field. Let's say B is pointing down. Okay, this magnetic field could be due to what? What could cause a magnetic field pointing down at this location? Okay, we could have a North Pole up here, right? Or we could have a South Pole down here. Anything else? Okay, if we had a proton moving to the right, let's see. If we had a proton moving to the right, where do you want the proton? Oh, behind it? Yeah. Okay, that's a little hard to draw here, right? But if you had a proton moving that way, And okay, so let's do this in 3D. Here's the direction of the magnetic field pointing down, right? And if you have a proton moving that way, V cross R, which would be towards you guys, right, would give my thumb pointing down, right? So yeah, you can have a magnetic field produced by a proton moving to the right, or a current, for instance, maybe a wire where we're looking at an observation location in front of the wire. So the idea is that you can have lots of different ways of producing a magnetic field pointing down at these locations. Okay, you could have a coil, right? You could have a coil with a current that would be, let's see, if the current were flowing, conventional current were coming out here and flowing around in front and going in, that could produce a magnetic field pointing down. Okay, lots of different ways. Well, we've produced this magnetic field somehow, and now I'm going to have another charge in this magnetic field. Okay, so let's say we have a charge moving to the right. Okay, this charge is not the charge that's producing this magnetic field. This is some other charge. Okay, so our magnet is, or our coil or what have you, is producing this magnetic field, and then I shoot a positive charge through it, and the velocity is in that direction. Okay, well, based on what we know about cross products, how would we find the direction of the magnetic force on that moving charge? Cross product says what? You have to point your fingers point the fingers of the right hand in the direction of the velocity, right? The first vector in the cross product. So everybody, fingers in the direction of the velocity. And I got to curl my wrist around so that I can bend my fingers in the direction of the magnetic field. The field due to this coil or this magnet or whatever it is pointing down at this point. So V cross B, it's going to feel a force pointing inward. So let's draw that. We have the magnetic field pointing down at this location. And then V cross B gives me a force pointing in that direction. That's the direction of the magnetic force on that charge. Okay? And I also have to worry about the sign. If I multiply V cross B by a positive charge, then the vector, what happens to the direction? Stays the same, right? So the magnetic force is, in fact, in that direction. What if it were an electron moving in the same direction? What would be the direction of the force? It'd be coming out, right? Because V cross B is in, but you multiply by a negative charge, you get a force outward. Okay? So the force in that case would be out towards us. All right? Get the idea? Basic idea? Let's try a couple questions. What's the direction of the magnetic force on the proton? We have a proton kind of moving up and to the left. The magnetic field at its location is pointing to the right. Again, keep in mind, this is a magnetic field not due to that moving proton, but due to something else. What could be causing this magnetic field? Anything. Well, what could be over here? We could have a north pole over here. You could have a south pole over here, or some combination, right? So again, this is an external field, but we happen to have a proton moving through it. What's the direction of the force on the proton? Okay, so just about everybody says answer number 6. We have a proton, fingers in the direction of the velocity. V, got to kind of wrap my fingers around like that so I can curl them towards the second vector, and my thumb points into the page or into the screen, which is the negative z direction. Okay, so the force is going to be in the negative z direction. Great. Let's try another one. An electron is traveling in the negative y direction. At its location, there is a magnetic field in the negative z direction. What's the direction of the magnetic force on the electron? I would suggest you actually draw the picture in your notes. Okay, well, got to watch the sign, right? This is an electron. This is an electron, so you got to watch the sign flip, right? Yep, that's it. So let's draw it. Let's draw it. We have X and Y and Z coming out towards us, positive Z. So if I have a proton that is moving in the negative, or excuse me, electron moving in the negative y direction. So here's the electron, and its velocity is that way. And the magnetic field at that location is negative z. So B is pointing into the board. We say V cross B gives me positive x, but I multiply by the charge of an electron, so the force is in the opposite direction, negative x direction. Okay, so the force is going to end up that way. Okay, so answer 2 is correct. Okay, so be careful of the sign. Just like when we were doing magnetic fields, you had to watch was the charge positive or negative. Same with magnetic forces, right? Is the charge being affected positive or negative? Okay? Yeah, question. If you want to do that, if you can remember that, go right ahead. I would, sure, it would work because you're doing the sign flip, right? You're saying the right. If you want to keep an extra step in your head of remembering what hand to use depending on the charge, feel free. But if you mix them up, don't come crying to me, okay? I like to just say, look, any cross product is going to be a right-hand rule. But again, just think about the formula here. You're multiplying by some scalar. If it's a positive scalar, then the vector you get is going to be in the same direction as V cross B. If it's a negative scalar, the vector you get is going to be in the opposite direction. Okay? Other questions? Let's try one more. A proton is traveling in the negative x direction, and it experiences a magnetic force in the negative z direction. So we know the direction of the force. We're trying to work out a possible direction of the magnetic field that causes that force. So it's sort of the reverse question. If you know the velocity and you know what the direction of the force is, what could have been the direction of the magnetic field? Okay, we've got a majority answer that says answer 3, positive y direction. Let's test that out. If we have a proton here, and the proton is moving in the negative x direction, so the velocity is that way. If we have a magnetic field in direction 3, the positive y direction, so let's say the magnetic field of that location is that way, will that give us the correct direction of the force? We say V cross B, thumb points in the negative z direction, which is what we stated, right? So force in the negative z direction, that will work, okay? And we don't have to, again, it's multiplied by a positive charge, so no flipping of the hand here. Force is in that direction. Is that the only possible direction for the magnetic field that could cause a force pointing in the negative z direction? What else could we have? Anything? Yeah, I see a hand move going from here to here, right? Anything that has a positive y component, right? So if I have a magnetic field, let's draw it in the same color here. If I have a magnetic field in that direction, right? V cross B, thumb points in. If I have a magnetic field pointing in that direction, V cross B, thumb points in. What if I have a proton in that direction, proton moving in the negative x direction, and the magnetic field at that location is pointing in the positive x direction? What's the force? It's 0, isn't it? Because if you take the cross product of a vector or two vectors that are in the same direction or opposite directions, so the same thing with if B were pointing that way, you get a cross product equal to 0, right? And we could show that by looking at the magnitude of the force. The magnitude of the magnetic force is going to be, well, the magnitude of the charge times the magnitude of the first vector times the magnitude of the second vector times what? Sine. Yeah, sine of the angle between those two vectors. So if the angle is 0, sine of 0 is 0. Sine of 180 is 0. Okay. Let's try another. So here's a current. Here's a wire. And it's got a conventional current running through it. And we've got a proton moving parallel to the wire in the positive y direction. And it experiences a magnetic force in the negative x direction. What's the direction of the conventional current in the wire? So you have to think through a couple steps in reasoning here. Talk to your neighbors, see what you think. Okay, well, we've got a majority answer. That's good. Positive y. Let's try it out. If we have a current, conventional current, it's going in the positive y direction, what's that going to do? That conventional current is going to do what? If you have a current moving, it creates magnetic field. Okay, so we need to think about the magnetic field at the observation location of the moving proton. So here is the velocity of the proton. And I want to think about what the direction of the field is due to the current at this location. That's going to give me a magnetic field pointing in what direction? Wait, let's try this again. Forget the proton for a second. Here's an observation location in the same plane here as the current. What's the direction of B? What's the direction of the field made by the current? Into the board, right? And you can get that a number of different ways. You can say I delta L cross R, thumb points in, or you can say thumb pointing in the direction of I, curl your fingers around, fingers curl in at that location, right? So we're going to get a magnetic field pointing in. All right. Everybody okay there? That's nothing new. That's old stuff. Okay, so now we have a proton here in the presence of a magnetic field pointing in, and the velocity is upward. So the force on that proton is going to be QV cross B, right? V points up, curl the fingers in, thumb points in the direction of the force that we want, okay? And then when you multiply by a positive charge, you still get the same direction. So it's got to be that, right? It's got to be a current flowing in the positive y direction. If it were in the negative y direction, the field direction would be reversed, and therefore the force direction would be reversed, okay? Questions here? Everybody okay?